Final exam review for Unit 2. Let's begin. When we began Unit 2, Lesson 1, we talked about arithmetic and geometric sequences, specifically their formulas. What I want you to recall is that if I'm looking for an arithmetic sequence, that means a sequence that adds or subtracts. The formula we'd be using is AN equals AK plus D times the values of N minus K. And in this, AN and K are counting numbers because they're terms in a sequence, term 1, term 2, term 3, and so on. So where N and K are elements of the natural numbers, meaning you're not going to get find the A 2.5 term. You're either finding the second term, A2, or the third term, A3, and so on. So those are natural numbers. That means natural numbers are the ones like you count. So we wouldn't have numbers such as like 2.5 or negatives. That was our formula. And I'll remind you, if you needed to find the common difference, what you could do is you can take and subtract here. And so if you subtracted, you'd have AN minus AK would equal your common difference times N minus K. Okay, that's how you could solve for your common difference. Now, when we talked about geometric sequences, what changed is now we're not talking, we could use the letter A, but I'm going to use an N here, a G for geometric. So the nth term of a geometric sequence is equal to GK. So it starts the same exact way, notice, but instead of adding, we're now multiplying. And so I'll multiply by the value of R, and I'll raise that R to the power of N minus K. So notice the formulas are almost exactly the same, except arithmetic adds, geometric multiplies, and once again, N and K are natural numbers. And natural numbers, that's so ugly. Let me try this again, and I'll do it like the way I did before. If you had to find your common ratio, what I would remind you is you could just divide by GK, and so you'd have GN divided by GK is going to be equal to the ratio raised to the power of N minus K. And you could use that to solve for your common ratio. Now that was lesson 2.1. 2.2, we compared those to this being very similar to linear functions, the geometric being very similar to exponential functions. And then we began with exponentials. So lesson 2.3, we really started focusing on exponentials. And this is an exponential here. And then on 2.9, we started with logarithmics. For this one, it says, what type of function is shown in the graph? This would be an exponential function. Now, how do I know it's an exponential function? Well, the easiest way to tell is to look at the asymptote. So exponentials and logarithms each have an asymptote. In this case, the asymptote for this exponential function can be found here at y equals 0. That's the horizontal asymptote. Now, how can I tell it's a horizontal asymptote? If I took a limit as this graph traveled to the left, you would notice it's approaching the y value 0. It flattens out. It approaches that value y equals 0. So if I just called this f of x here, I could write a limit, which is, there's a horizontal asymptote y equals 0. I've done that part. The end behavior would tell me that if I wrote a limit as the graph traveled to the left, as x approached the left, which would be negative infinity, the y's values, notice they don't rise, they don't fall. What they do is they get really flat and they stay flat with the y value of 0, that horizontal asymptote value. Now, what happens as the graph travels to the right? The end behavior of this graph f of x, as the graph approaches the right, as we continue on right without bound, meaning continue on forever, this graph rises and it rises to positive infinity. Okay, so this limit here, I'll call this a 2, represented by this end behavior, and this limit over here, let's call this one 1. This would be limit 1 over there. Okay, let's look at the next graph. Now this graph is not exponential. Now how do I know it's not exponential? Is I'm looking once again at the asymptote. I'm going to change colors this time to make this easier to stand out. We have a vertical asymptote this time. So this must be a logarithmic function. We have a vertical asymptote. We have a vertical asymptote, and so the equation would not be y equals, since it's a vertical, the y's values are always changing along this line, but what's constant is that I'm on the x value of 1. And so that would be my horizontal asymptote. Now on this graph, if I were to write its, let's see, that's the asymptotes. We did not placed here that this is a logarithmic function. Let me put that down there, logarithmic function. If I wanted to describe the two limits for the end behavior, this first limit here, and I'll call this function g of x. So the limit here of g of x as x approaches, now notice x does not go left forever without bound. It's approaching this value 1. It's approaching 1 and it's doing so from the right side. So you do a 1 plus. As we approach 1 from the right side, the y values increase forever without bound to positive infinity. Now what happens on the second limit over here? Well, on the second limit, x does increase without bound, meaning it goes right forever. Oops, we're doing g this time. Here we go. As we approach positive infinity on the x values, as they go to the right with increase without bound, the y values are falling. So they fall to negative infinity. And so notice the difference here between the logarithmic and the exponential in the previous problem. A logarithmic, you're always going to have negative infinity to positive infinity on my limits, whereas you'll have on the x values, that's the y's, I'm sorry. On the x values, you'll have a constant and you'll have an infinity. Exponential, since they're the inverse, notice we had our constant here as a y value with an infinity, but the x is one's negative infinity, one's positive infinity. So we switch off between those two because they're inverses of one another. Here, one more thing I could add that I didn't ask, if I wanted to state the range here, the range is all reals. The y values, it's from negative infinity to positive infinity. Notice there's no break in this graph from negative infinity to positive infinity, but the domain is not all reals. The domain would be from from 1 to infinity. 1 to infinity. Whereas in an exponential, notice it'll be different. The domain will always be all reals. The domain would be all reals because you go from negative infinity to positive infinity, negative infinity to positive infinity. However, the range would not be all reals. This is from 0 to infinity. And since it's an asymptote, we don't actually attain that asymptote. It would be a parenthesis around that. So just kind of note the differences between exponentials and logarithms. Now to go a little quicker here, what is this function? I see it kind of looks like a logarithm until I pay attention to its asymptote. When I look closely at its asymptote, I notice that the asymptote is a horizontal asymptote here, which means it's going through the y-axis. And since my horizontal asymptote is going through that y-axis, this must be a exponential function, horizontal asymptote. And this horizontal asymptote is at y equals 2. And so we said this is a exponential function. It's exponential because of the horizontal asymptote. And we have two limits here. Just to be quicker, I'm just going to write limit here. We'll call this h of x. The limit of h of x as we go to the right without bound, as we increase without bound, this gets flat on the value 2. And over here, this limit, no, not if, sorry, h of x, there we go. Which direction do we go forever? Left? Do we go left forever? Yes, we do. So to negative infinity, notice the y's fall as well to negative infinity. This will not be all reals. Notice that an exponential will have a y value that's a constant with an infinity, but the x's will be positive to negative infinity. Okay, and I have one more here. Look for your asymptote. Notice that the asymptote this time is vertical. Since it's vertical in nature, that means this has to be a logarithm. The x's are not all reals. The x's, we have a limited domain, a restricted domain here. So it is a logarithmic function. And this is a vertical asymptote, just say VA. It's y equals negative 1, 2, 3, 4, 5, negative 5. So if we wanted to write our limits here, this limit, we'll call this one k of x. this graph k of x, the limit of k of x. Well, what's happening here is we are increasing without bound on our domain, and the range is also increasing without bound. It's increasing. Over here, our domain is not unrestricted. It is restricted. We only can approach -5. This is far left as we can go, and we do so from the right side. And the y's fall as we get closer and closer as we approach -5. The y's are falling. So that would be our in behavior there. So that's the difference between logarithmic functions and exponential functions. Look for that asymptote. Now, how will the end behavior of exponential functions always be described? Well, no matter what, you will have on an exponential limit, I'm just going to say exponential like that. X, you'll have 1 going to -infinity, because remember, this is all reals. So you'll have 1 going to -infinity, and the limit of the other exponential will be going to +infinity. So you'll always have -infinity and a +infinity. And then over here, well, this is where we'll be different, is 1 will have an infinite value. It'll be the absolute value, well, it'll be either positive or -infinity and a constant. So 1 value here, 1 value there, 1 will be constant, 1 value a constant, the other either a positive or a -infinity. And then on a logarithmic function, this will be slightly different, but since they're inverses, you would exchange your x and y. So on a log, you would have x approaching the y. Well, you'll always have 1 being a -infinity, and you'll also have another limit where the y's approach a +infinity. That part will always be true, but what changes is your x. So 1 value, typically, and without a transformation, typically 1's going to be infinity, but we'll just say like this just to keep it as a beautiful inverse of one another. 1 value is a constant. Oops, forgot the L. 1 value is a constant. The other is plus or minus infinity. So there's a relationship for the end behavior between logs and exponentials. Now moving on. Look at this table here. It says what type of function could be described in the data? Well, I can quickly observe when looking at this, the x's go from 1 to 3, 3 to 9, 9 to 27, and over here 0, 6, 12, 18. I can see quickly that these are changing additively. These are being added by 6 each time, added by 6, and added by 6. And the x values are actually multiplying. This is a straight multiplication. This is a really simple one. I am multiplying by 3 every time. Each value gets multiplied by 3. Which tells me when I see that this is a logarithmic function. Logarithmic has x's changing multiplicatively, and your y's changing additively. That's a logarithmic function. Now, what equation would best fit the data? Now, here's how, using a log function, your general form is going to be something along this line. A log, you might remember us working on this, b to the x minus h plus k. And truthfully, we could have a transformation there, but we don't usually see that, so I'm going to leave that blank now. What you would do is you'd begin, oftentimes, if you have no transformation, well, let me start with the thing that's always true. What you're multiplying by is going to be the base. This is telling you the base equals 3. So for the formula, I'm going to substitute a b equals 3. So here's what I can do right off the bat. I know I'm going to have y equals a log 3 x minus h plus k. That part I know is true. Oftentimes, this will become a. Not always, but oftentimes, if you want to put there, without a transformation, this becomes the a. Oftentimes equals a. Now I'm just going to put that. Doesn't mean it always is true, but if you're running out of time, just guess that's a. That's what I would tell you. Guess that's a. So what we could do is we could plug in some values. And here's what I know. This is 3, each one of these is 3 to some power. So if I had an x value of 1, that comes from the power of 3 raised to what? 3 raised to what? 3 raised to what equals 1? And the answer is this is 0. Now, why does that matter for me? Because what I can do is once I figure out that this is 3 to the 0, and that's equal to 1, what I can discover is there's no horizontal transformation because 3 to the 0 should be 1. I'm not getting a weird value, like these are lining up like they should be, meaning it's not numbers like, let's say there was a horizontal, like if I had an x minus 1 on the inside, remember minus 1 would do the opposite, so you'd actually add. Like if it looked like 2, 4, 10, 28, you would look at the table and you'd say that's being multiplied by 3. 2 doesn't become a 4. That's 2 times 2. Well, this is not 2 times 2. You'd say it's not, there's been a transformation, the translation of some sort. Well, that's not here because 3 to the power of 0 is 1. So here's what I just discovered. By that, I can say, therefore, h equals 0. H equals 0 since 3 to this power, because remember, we're doing a log, so you're actually going to exchange it. 3 to this power equals 1. Let me do this. Let me slide this over. H equals 0 since. So here's what I now know I have. I have y equals a log 3x plus k. So I've simplified my equation to that. Now I'm just going to plug in some points. Okay, now I could plug in the point 1, 0. And so if I plug that in, 0 is the y. Let's plug in. So I'm going to plug in 2 points is what I'm going to end up doing to solve here. So 0 equals a log base 3 of the x is 1 plus k. Well, this is saying 3 to what power is 1? Answer is 0. And so that cancels out. And so 3 to the 0 power is 1. So that's 0. So if I simplified here, I have a times 0, which is nothing, plus k. 0 is k. Well, that's great news. Now that I know that k is 0, I can take that back up. And now I can plug into our equation. So we've gotten to here. So now I'm going to say y equals a log 3x. I don't need the plus k anymore. And I plug in another point. And so the second point I'm going to plug in now is I'll plug in a 3 and a 6. So 6 equals a log 3 of 3. Well, log 3 of 3, that's saying 3 to what power is 3? The answer is 1. So 6 equals a. And with that, we have got all of our answers that we needed. We had this over here, and we've now solved the problem. The equation would be, I'm going to call it f of x because that says f of x there. The equation becomes f of x equals 6 log base 3 of x. Now that was a lot there. So I'm going to and I'm going to show you oftentimes this, I said this is equal to a, and it was in this case. So this point, notice that those ended up being the same. And oftentimes that will be true. Not always, but oftentimes. So let me work through another problem. Oh, and I need to erase something so that someone checking the notes later, that needs to be gone. That was when I was messing with the data there. Okay, now let's look through another one. Let's say we're looking at this equation. This time what I notice is happening is I'm adding 1, adding 1, adding 1. So the x's are always adding by 1. But if you look at the y's, it's hard to tell. So what I'm going to do is I'm going to create a rock table. Because right now, my table's not looking that great. A rock. So what do I change to go from here to here? Well, I'm increasing by 1. And then here I increase by 2. And then here I'm increasing by 4. And then here I'm increasing by 8. So what happened is I must have a transformation here because when I look over here, I can tell real easily, oh, I see what's happening. This is getting multiplied by 2. This is getting multiplied by 2. This is getting multiplied by 2. So what I have here is an exponential function because the x's are being added by 1 whereas the y's are being multiplied. So this is an exponential function. I can establish from here the base is equal to 2. So for our problem, we'll have a b of 2. I'm going to go ahead and just set this up. And remember what I said, oftentimes this becomes a. So we're going to say right here, oftentimes, not always, but oftentimes our a will equal 1, since that's what we got right there. So let's go, this is exponential. The parent function for exponential would look like this. Y equals a times b to the power of x minus h. Let me put it in parentheses. X minus h with a plus k on the outside. So I'm going to begin here. Since I know I'm multiplying by 2, this first value is 1, which is equal to 2 to the power of 0. Now, since it's 2 to the power of 0 is 1, and I check out my x's, and that's a 1, I have no translation on h. Since this is true, since 2 to the power of 0 equals, no, this 1 right here. 2 to the power of 0 is supposed to be 1, which that's true. I don't have any transformation here. This part's good, but this is off. I have a 1, but this actually says 4. What's happened is from the AROC, this value is 3 greater. So really, this is the AROC plus 3, if you will. Or maybe I should do AROC, and if I added the 3 to that, I would get AROC plus 3 would give me this. That would become equal if it was AROC plus 3. Notice that? So what that's establishing is that our k is going to equal 3. So I'm going to come over here and I'll put k equals 3 there. Okay, so hopefully that's making sense what I'm doing so far. Now I know the base is 2, so I could also plug in, let me actually do this. So for the sake of notes, so that parent function's there. Let me do it on the next line. We know the base is 2. So y equals a times 2 to the power of x minus h. And we now know this is going to be plus 3 on the outside there. Okay, so how do I continue on from here? Well, I plug in some points. Okay, so if I plug in any one of these points, oh, and I already said, I'm sorry, one more thing. H is 0. How do I know h is 0? Because this is 2 to the 0, which is this value, equal to 1. Since these two matched up, this is also saying h equals 0. H equals 0 since 2 to the 0 equals 1. And I'm getting that from here and from there. So let me come back one more time. It's just going to be 2 to the power of x, like that, plus 3. Because 2 to the power of 0, which is the x, we didn't have to change the x, gave us this 1, which is what we needed. All right, so continuing on, I got to plug in 2 points. So if we want to plug in 2 points, I'm going to use 0 and 4 here. If I plug those in, I have 4 for the y equals a times 2 to the power of 0 plus 3. Well, 2 to the 0, anything to the 0 power is actually 1. So I'm saying 4 equals a plus 3. Therefore, a's got to be 1 since if you subtract 3 from both sides, what are we left with? We're left with 1 equals a. So now we have that value. So come back over here. And now I want to say y equals 2 to the power of x plus 3. And I got my answer. I have all the values I need. I have here h equals 0. Since 2 to 0 was that AROC value of 1, we found out k is 3 because it takes the AROC plus 3 to get back to the y of 4. I had the base of 2, and we solved for a. I only had to plug in one value. This is my equation right there. And you can check with any other value if you wanted to. Let's just do a quick check. And I could plug in any value. I'm just going to choose 311, just a random value. 11 would equal 2 cubed plus 3. Let's check that out. 11 is 2 cubed is 8 plus 3. That works. That's good. Okay, I didn't verify this one. We could have verified. Again, you could plug in any number to plug in. If I just, this time I'll choose 3 and 6. If you plug in a 3 there, log 3 of 3. Oh, I already plugged those two in. Sorry, let's plug in the one we haven't plugged in. If I plug in a 9, 3 squared is 9, so that's a 2. 6 times 2 is 12. And notice if you plug in a 9, you're supposed to get a 12, so it would work. Okay, I'm gonna speed up a little bit to check this one out. Notice what is going on this time. I'm adding one, adding one, adding one, adding one. So is it a logarithm? No, because logarithms do not add, they multiply. And so this time I'm looking, what am I multiplying by? It's hard to tell. Let's do an AROC column. To find out, I can see this is going to be exponential because this is multiplying by something, but I'm not sure what it's multiplying by. And so I can see to go from here to here, I need to add 1. And then from here to here, I'm adding 3. And from here to here, I'm adding 9. And from here to here, I'm adding, what's that, 27. So now I can state, oh, I see the base that I'm multiplying by 3 every time. I'm multiplying by 3. So therefore, my base equals 3. So I'll write this for our equation. We know now that that's true. And like I said, oftentimes this will be A. That doesn't mean necessarily it will be A, but oftentimes this is going to be A. Now we'll check that later. I'm not going to write it down because I kind of know what's going to happen on this problem. But this is, by the way, an exponential function. Whoops, exponential function. Now, if you wanted to assume something, so we could say oftentimes it's A, but it's not going to be this time. Let me show you why not. So what do I know? My base is 3, so that means 3 to the power of, wow, no, 3 to the power of 2 is not actually 1. It's supposed to be 3 to the power of 0 is 1. And so I have a problem here. Remember, it's 3 to the power of 0 equals 1 is what I need this to be the AROC. Now that's a 2. Now how do I get from 2 to a 0 is I would have to actually come over here and have like an x minus 2 column. Whatever x minus 2 is, that would give me the 0. So this value right here, these columns are too high. And remember, x's are liars, so I'm taking away 2. So when you write the parent function, is exponential, a times b to the power of x minus h plus k. Here's what I know first off. I'm going to have an x minus 2. I just realized that, or that h is negative, that h is going to be a positive 2. What does that mean? That means this is 2 bigger than it's supposed to be. This value was supposed to be a 0 to get it 1, but it's a 2. It's too high. That means I have x minus 2 because that's a liar. So as I start to plug this in, here's what I know. I don't know a. I do know my base is 3. Let me do parentheses. And I'm going to have x minus 2. That part I now know. Now I don't know k yet. So you could try to subtract, but we don't know a either. So what am I going to have to do? I'm going to have to plug in some values. I'm going to first plug in these points. So when I plug in the first point, I have a negative 0.5 equals a times 3 to the power of 2 minus 2 plus k. Well, 3 to the power of 2 minus 2, that's the power of 0. Anything to the power of 0 is 1. So I could simplify that and say, oh, that's just 1. So I have negative 0.5 equals a plus k. Well, I can't solve anything yet. So what I'm going to do is plug in another point. I'm going to plug in this point here. And so I'm going to say 0.5 equals a times 3 to the power of 3 minus 2. I plug in a 3 and a 0.5. That's all I've done, plus k. And when I go to simplify this, that's 3 to the power of 1. So it'll be 0.5 equals 3a. 3 to the power of 1 is 3. So 3a plus k. Now what I'm going to do is I'm going to subtract these two equations from one another. I'm going to take this equation and I'm going to subtract this. So I have the negative 0.5 equals a plus k. I'm taking this equation right there, but I'm going to subtract it. So what happens is 0.5 minus a negative 0.5 becomes 1. Two negatives make a positive, so 0.5 plus 0.5 is 1 equals, I'm subtracting here, so 3a minus 1a is 2a's. K minus k goes away, and that's the reason I subtracted, is to cancel the k. Last step to get a is I divide by 2. And now we can state confidently that a is 1/2. Okay, so oftentimes this is a. Is it actually a this time? No. We found out a is 1/2. So the only thing remaining to find is, what is k? You can take any equation. I'm now just going to go plug this into this equation right here. And so negative 0.5 would equal 0.5. That's a, 1/2, plus k. I subtract that. I subtract this 0.5 here, and we'll finally have k. Negative 0.5 minus another 0.5 equals -1. -1 is our k. And now we have our equation. So putting it all together, this is called g of x. I'll say g of x equals, our a was 1/2. Our b was 3 to the power of x minus 2 minus 1 on the outside. There's your equation right there. Now I'm going to go through this one more time. So we look here. Well, what's happening? Well, the easiest column to figure out is not this one. That adds 2, that adds 4, that adds 8. That's not adding the same number, but this is adding the same number. I'm adding 2. I'm adding 2. I'm adding 2. I'm adding 2. That's oftentimes going to be the a. We'll find out if it is here. But notice over here, that's not doing it right, and it's not multiplying. I can't say 3 times 2 is 5. That's not true. 3 times, and 5 times 2 isn't 9. That doesn't work. So what I'm going to do is come up kind of with an AROC column here, if you will, kind of like the AROC column here, and say, well, now what's changing to get from 3 to 5? Well, it's increasing by 2. What about from 5 to 9? I'm increasing by 4. From 9 to 17, I'm increasing by 8. And finally, 17 to 33, I increase by 16. Notice that's a base of 2. Everything's getting multiplied by 2. And this is getting multiplied by 2. This is getting multiplied by 2. This is getting multiplied by 2. Therefore, the base equals 2. And for an equation, we're going to have a base of 2. Now, this is a logarithmic function. And so our base equation would be y equals a log base of x minus h plus k. Now that's the equation we're going to work into. We already know the b is 2. So now let's come back up here. Notice that's multiplying by 2, which should be 2 to the first. That should be 2 to the first power. And as I look at it, 2 to the first, it's not matching up right here. These values aren't correct. So something's going on, because 2 to the first is not 3. Notice that would be 2 to the first, 2 squared, 2 cubed, so on. We're starting off at a 1. So what does that mean for us? Well, it means this x value is 1 too big. Notice what's happened here is it's supposed to be 2 to the first, which would be 2, but 2 to the first is not 2. 2 to the first, 2 to the first is not 3. 2 to the first is 2. This is 1 too big. This has been added by 1. Or just to state it better, it's not that this table is wrong. I mean, that was the x value that they gave us. Really what I should say is over here, this is x minus 1. That would make this 2. That would make this 4. So on, so forth. So 2 to the first, and now we're set up right. So that's my h. My h is going to be 1 here because I'm 1 too big. My h is going to be 1. Remember, inside lies. And so here I'm subtracting 1 in the equation. What that means is h is actually 1, but the value here will be a -1. Go back here. Let's go back. Let's see. You remember here we had x minus 2, and I said that made an h of 2. It's the same concept here. So I had an x minus 2 in the equation, but it actually meant I add 1 here. Since I actually add 1, get to the first 3, that means my equation is going to be x minus 1. So I can fill that part in. So we fill in y equals, we have no idea what a is. We could guess that it's 2, but we don't know for sure. I do know my base is 2. And I now know in this parenthesis, I'm going to have x minus 1. Because to get to my data right, I need to take away 1 from what they're showing me there, plus k. So now I'm going to plug in some points to find out what's going on over here. Okay, so let's plug in the first point they give us, 3, 5. So 5 would equal a log 2 of 3 minus 1 plus k. Well, whoops. When I plug that in, 3 minus 1 is 2. So log base 2 of 2, that's just 1. So what I really have is 5 equals 1a plus k. Well, that's nice, but I can't solve anything yet. So I plug in another point. This time I'm going to plug in 5 and 7. So I'll say 7 equals 5 log base 2 of 5. So that's this 5 going in. Why did I put a 5 there? That's an a. I'm sorry. A log base 2. This is now where I put the 5 minus 1 plus k. 5 minus 1 is 4. So 2 to what power is 4? The answer is 2. I evaluate that log, I get 2 there. So 7 will equal, this is a times 2, or said another way, 2a plus k. Now again, what I'm going to do is solve these two equations together. I want to eliminate the k, which means I'll just subtract this equation. So I'm going to take this equation and I'm going to subtract it. So I'm subtracting 5 equals a plus k. And so 7 minus 5 is 2. 2a minus a is a. K's just go away. We now know a is 2. We're getting really close to being able to solve. Now I'm going to plug this into any equation. I'll plug it into this one. It's easier. So we have 5 equals 2 plus k. Subtract your 2 across, and we have our answer. I subtract by 2. I get that 3 equals k. There it is. So we found all 4 values necessary. So I can write my equation. This one is titled f of x. So I'll say f of x equals, a comes first. There's a2. So notice that matched up. This was oftentimes a. It was this case. It turned out to be a. Oftentimes equal to a, and that proved true this time. 2 log, the base was 2 from over here, base 2, x minus 1. We got that because this was 2 to the first, 2 squared, 2 cubed, but that wasn't matching up there, so we needed to subtract 1. And the k we found out was plus 3. That 2 to the first should give us a 2. We needed to add 3. 2 squared is 4. We needed to add 3, and so on. Just to get the values right over there, if that makes sense. So, anyways, there's our equation. You could verify with any other point if you wanted to. You could plug in, I don't know, 17 and 11. 11 equals 2 log, and you plug a 17. 17 minus 1 is 16. 2 to the 4th, 16. So 2 times 4 is 8 plus 1, 11. That's what it's supposed to be. It works. All right, putting all that aside, let's move on. What if you had to solve? How can you solve? Well, a lot of this comes down to properties. And I want to change one thing just to make us do an extra property. I'm going to move this right here. Let's say the problem looked like that. Well, how could I solve if I was given these values? Well, I could take log base a of a to the 5th. And I can first off do a power property and say that is 5 log BA, which is exactly what we started with before I changed that. But I just did that so I could write down another property. That was the power property. And now what I could do, if I need this to be a natural log A, natural log B, and notice I'm not as a natural log, I'm log B right now, I could do the change of base. I could say this is 5 times, and when you do a change of base, you can change it to logarithm of any base you want. I want the natural log of base of E. So natural log of A divided by the natural log of B. So what I did there is a change of base. When you change your base, what was the base goes to the denominator. What was originally the number inside the logarithm becomes the numerator. And you change your base of the logarithm to whatever you want it to be. I'm going to choose natural log because that's what I'm given here. And so let's write this down. This is change of base And I'll just say property PTY. Okay, now what can I do with that? Well, I can substitute. I know what natural log A is. I've already used purple. Let's use a different color here. I can say natural log A is equal to 2. And this is divided by the natural log of B, which is 3. And we have our answer just like that. When I multiply 5 times 2 is 10, and I divide that by 3, but it does not simplify. There it is. There's your answer. It's 10/3. So let's let you see another one of those. Okay, what if log base 3 of A is 2, log base 9 of B is 3? Evaluate log 27 of A times B to the -2 power. Okay, well, first I'm going to write this out. What properties can I do? I can see I need to change the base at some point in time. But before I do that, I'm going to look at my powers. Well, and my product in here. Now, I have a power of -2, which I would like to move out front. The problem is -2 does not connect to A. That's why I wrote it this way with a dot. These are multiplying. Before I could do anything, I had to change this multiplication. And so I'm going to do the product property. You could also say this is quotient, because technically that's A divided by B squared. Note, I can note this. You could do it this way, A over B squared, and do the quotient property if you like. But either way, we'll get the same answer. So it's log base 27 of A plus log base 27 of B to the -2. And that was using the product property. Say PTY. Now what can I do from here? Now I'm going to do the power property. So I'm going to take this -2, move it to the front. It's going to multiply in the front. And so this would equal log base 27 of A minus 2 log base 27 of B. Notice what I said earlier about how you could have done this as quotient. But the way I did it here, this is a power property. So can I substitute? Well, not quite yet. I need this to be log base 3 of A. So let's do the change of base property. Now we're going to do this change of base property twice. So this first, I'll do in blue. This becomes, if I want it to be a base of 3, then the A goes to the numerator, and it's going to be divided by log base 3 of what was originally the base, 27. And this is a change of base. Change of base property. But I don't just do it there. I also do it here. It's going to be -2. And I need this log to be base of 9. So I'm going to say log, instead of 27, 9. That's an ugly 9. 9 of B divided by log 9 of 27. Notice it's now a log of B divided by a log of 27. You can pick your base. I chose base 9 because that's what I need here. That was a change of base property twice. We did that change of base property twice. Okay, so what can I do from this? Well, picking back up, different color here. I can start evaluating. I know log base 3 of A is 2. So I can say that's 2 over log base 3 of 27, which we will evaluate that in a second, minus 2 times, we have log base 9 of B, which we know is 3, over log 9 of 27. And so if I wanted to evaluate this, 3 to what power is 27? Well, 3 cubed is 27. So this is easily 2/3. We can say that confidently. Because 3 cubed is 27. That's where I get that. That's a 3. Now, this one's not as easy. If you try to do upside down division to find out 9 to what power gives you 27. Well, 9 goes in 3 times. But the problem is, it's not the same number. And so I need to break down 9. And so what I find out is it takes 3 powers of 3 to get into 27. And it takes 2 powers of 3 to get into 9. So this is 2/3. So this is minus 2 times 3 is 6. But down here, this is going to be not 2/3, I'm sorry, 3/2. 27 is 3, 9 is 2, like that. And you could break that down. You would change your base if you wanted to. Log base 3 of 27 over log base 3 of 9, and you would indeed get 2/3 there. So 9 has 2 3s, 27 has 3 3s, it's 3/2. because the 27 is above the 9. Okay, I want to reduce this. So what you can do, if you're dividing by a fraction, is you can flip the denominator and multiply. So this becomes over 2/3 that way, which means I have a common denominator. My denominator is 3, so it's 2 minus 6 times 2 is 12. Therefore, my final answer is negative 10 divided by 3. Ironically, we just got positive 10 over 3. Now we get negative 10 over 3. All right. The graph shown is called a, now what do we call this type of plot? This would be called a semi-log plot. A semi-log plot. What transformations occur for the data to be placed in this graph? Well, I can see that these are counting by powers of 10. So what I did is I had to do this. I'm taking a common log of the y values. So what transformations occur for this is you take a log, a common log, that means a base of 10, of the y values. That's how you would find this graph. So whatever your equation was, you take a log of both sides. That's how you place your data on there, is we're taking a log of the y values. So if I wanted to graph something, let's try this one. I'm going to come up with a table here. How about this? X, and so we don't forget it's y equals 2 times 4 to the power of x. If I plotted some points, let's say 0, 1, 2, 3, and maybe I'll do one more, 4. If I plug those in, 4 to the power of 0, that's anything to the power of 0 is 1, so that would be 2. 1 times 2 is 2. If I plug in a 1, 4 to the first is 4 times 2, that's 8. Notice what's going to happen is I'm going to multiply by 4 every time. So this should be a 32. Let's check. 4 squared is 16. Double it. Yep, 32. Multiply that by 4. 32 times 4 is 128. And if we multiply that by 4, we would get this value, which would be 512. So I come over here to plot the points, 0, 2. Here's 0. This is 1. Be careful. This is 2. That would be 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there is 0, 2. So now I go 1, 8. That's right there. 2, 32, 10, 20, 30. It's going to be just slightly above that 30. 4, 5, 12. How did I get off 2, 32? 3 is 128, sorry. 100, that's 200. It's going to be in here. 4 is going to be 512. It's 100, 200, 300, 400, 500, and 12 is slightly above it. Now, what is this? What type of function represents the appearance of this graph? It appears to be linear, if you ask me. This looks linear to me. Let me place this on there. Now, here's the question. Why does it appear to be linear? Well, because this was an exponential function. And remember what I said mathematically, what happens is you take a log of the y values. So if I took a log of y's, what I'm doing is I'm also taking a log of 2 times 4 to the power of x. So I'm taking a log of the y values. And what happens is if you take a log of an exponential, you can come up, it'll become a linear function. So by formula, the way this works is this equation right here. I'll just call it y hat. Y hat is going to equal the log of 4 times x plus the log of the a value, which was 2, and this is a common log, that's why I'm not putting a base. That's my y-intercept. So if you put that in there, you put all this, and that should be my equation of my line over here. Its appearance, it should look like this. Now, this is kind of a weird thing here to think about. Where's my graph? There we go. If I went to a document here, my y-intercept should be the log of 2 That would be my y-intercept. Now notice these are counting by powers. I want to remind you this isn't actually 10. When you're doing a semi-log, you're counting by powers. So what do I mean by that? That represents 0 here. This would represent 1. So the first point should be 0.3. Where is it? 0.3 of the way up to 10. Notice that that point is a 0.3 of the way to 10. Okay, if you measure the distance. This would be 10 squared and so on. This would tell you your slope, like what's the rise over run? Well, if you look at, if you consider this 1 and this, excuse me, this 0 and this 1, you'd say, well, it looks like it might be going up about half for every x unit it goes to the right. Well, let's take a log of 4 and see what we get. If I did a log of 4, come on, log of 4, here would be your slope. It's actually 0.6, so it goes up 0.6 for every 1 unit over. And so that's my equation there. That would be the equation of the linearization of this graph is right there. That's what the equation would be. And I did that by taking the log of the base, that's the slope, and the log of the a value is your y-intercept. Now let's look at some other things. What if g of x was equal to this log 9 of f of x? And g of x equals this. What is f of x? Could we solve? Well, yes, we could. So what I'm going to do here is I'm going to substitute in what I know about g of x. G of x here, I'm just going to substitute in, is 0.5x plus 2. And that's going to equal log 9 of f of x. So here's the question for you. How would I solve that? Well, I would need to solve for this log. What's the opposite of a log? It's an exponential. So I take my base and I would raise it not to f of x any longer, I'd raise it to this. What I'm going to do here is I'm going to make it look like this. So I'm going to raise it just to make it simpler like this. I'm raising each of these, or taking 9 as my base and raising it to that. So this 9 and the logarithm would cancel. So I'm left with 9 to the power of 0.5 x plus 2. And that would equal f of x. Now, that's not quite the equation they wanted in. They wanted it in this form. And so what I'm going to do is use some properties here. Is I can now say, I'm going to say f of x. F of x would equal 9 to the 0.5x. And since these powers are adding, this is a product property. I can say that's times 9 squared. That's the product property I just did right there. Product property. Whenever you have powers adding. Okay, now that 9 squared is 81. I can say 81 times 9 to the, and I'm going to use a product property, a power property, and say this is 0.5, and I'm going to put the x on the outside. Now that right there is what I'm doing is the power property. Is I can make my powers, I can break apart the factors of the power like that. So a power raised to a power, you multiply, and so I'm doing the opposite, factoring that. And now what is 9 to the 0.5 power? That's like basically saying the square root of 9, which is 3. So I could rewrite this as 81 times 3 to the power of x. There's my equation. F of x would equal 81 times 3 to the power of x. There's my answer. Okay, so what's the inverse of this function? Well, how would I find inverse? Well, I need to exchange my x and y. So if I'm looking for the inverse, I would switch x and y. So x equals 2 times 4, raise that to the power of y minus 2, subtract 3. To solve this, I need to isolate this exponential. So I'm going to add 3 to both sides. And so I have x plus 3 equals 2 times 4 to the power of y minus 2. And now from here, I could divide by 2. So I'll do that next. Since this 2 is multiplying, I'm going to divide by 2. Remember, when you divide, you distribute that. So I have x plus 3 over 2 equals 4 raised to the power of y minus 2. So now that I have this exponential isolated, what's the opposite or the inverse operation of an exponential? It's a logarithm. So I could just say it's the base raised to this, but what I'm gonna do is take the log of 4 on both sides. So I'm gonna take the log of 4, and here the log of 4 of all this. And so these 4s will cancel out. You remember you can move power property, move that to the front. That becomes log 4 of 4 is 1. So what do I have left over here? I have log base 4 of x plus 3 over 2 will equal, these will simplify, and I'm left with y minus 2 multiplying times this 1. Log 4 of 4 is 1. So y minus 2 would multiply times 1, and it's just y minus 2. Last part, I would add 2 to both sides. This needs to be outside the parentheses since I'm not adding inside the logarithm. And I have my inverse. My inverse f negative 1 of x would be equal to log 4 of x plus 3 over 2 plus 2. There's my inverse right there. So to try another one here, let's say this is y, and so I would say x equals 5 log 7. I'm finding the inverse again of 3x plus 1 minus 2. Whoops, I forgot to exchange. This becomes a y when I take an inverse. And so now I go through the steps to solve again. I'm going to add 2 to both sides. Trying to isolate the logarithm is going to be my goal here. So x plus 2 equals 5 log 7 of 3y plus 1. Next step to isolate my logarithm is I need to get rid of this 5 that's multiplying. So I will divide by 5 since that's the inverse. And so I have x plus 2 divided by 5 is going to equal log 7 of 3y plus 1. So what's the inverse operation of a logarithm? Well, it's an exponential. So what I'm going to do here is I'm going to raise it. It's going to be 7 raised to these powers. So these two cancel because what you can do, again, you could break this apart. You can do all kinds of things. But those two are going to cancel. And it's going to look like this. Once I have 7 raised to the x plus 2 over 5 equals, these two cancel each other out, 3y plus 1. So I subtract by 1, and it cannot subtract from 7 because the 7 has a power. That would be breaking PEMDAS. So 7 to the power of x plus 2 over 5 equals 3y, and then finally I divide by 3. And once again, I cannot divide only the 7 because of PEMDAS. And this is a g, so I'm going to call it g negative 1 for g. And the inverse of g is going to equal 7 raised to the power of x plus 2 over 5, all divided by 3. There's my equation right there. You know what? Another way I could write this, since it's an exponential, is I could just do a 1/3 in the front. That's my a value. And so dividing by 3, you could say that my a value is 1/3. My base is 7, and all that in there, some other transformations. So there's your inverse function.